Now, it seems really strange and easy to say that, oh, this particular concept runs and just rules everything. It does. In this case, it does. Talking about balls rolling down hills, the metabolism inside your body, photosynthesis, all the real complicated things that happen in nature. What is natural? It's all thermodynamics. It's all governed by thermodynamics. It's how we understand. This is how we predict, oh, this enzyme is going to do that. Or this cannot happen, this can happen. Whether it's inside a cell or a chemical system or trying to make a product or trying to do a process. You can say whether it's possible or impossible. Or just how likely it is. How natural is it? That's all thermodynamics. So it's really powerful stuff. Now, we're going to stick to just the chemical area of it, but you don't have to. You could use this for engines. You could use this for anything that's natural. I went to the Smithsonian Museum, and I took a picture of... What's that? No, you can take pictures. No flash, right? But I don't think they even care about the science part. No one cares. Now, there's in the art part about how no flash. And one thing that did bug me, now first off, I am a cheapskate big time. That's why Washington, D.C. and I fit like a glove. All these are fantastic, free. So one thing that did bug me is I went to the art area. I mean, they have Picassos. They have all these fancy, really top-notch, priceless, paintings, right? You can walk up with your soda and right? They let you get as close as you want to these things. Isn't that messed up? There was this guy walking around with his Pepsi and his drink, walking, right? What if he spilled? Isn't that ridiculous? That stuff should be behind sealed cases. I can look at it just as well behind a sealed case. Anyway. Cheapskate, because all these fancy museums are free, right? Okay, so here's a perpetual motion machine in this photograph. Now, it wouldn't be much of an exhibition if things weren't moving. So the little guy's always moving, perpetual motion machine. But, you can see, but right there, it's plugged in. Right? It's plugged in. You can never get something for nothing. That's the whole first law of thermodynamics. Work output can never be greater than the work input. But I like the idea. So according to the first law, perpetual motion machines are impossible. They can't happen. There's no point in even trying. You can't get something for nothing. Okay? Oh, they worked with all these weights and, I don't know. Someone spent a lot of time and energy on that. But it rotated. It rotated. I guess the idea is to make it perfectly balanced. I don't know what the idea is. Anyway, it's impossible. The first law has an equation. Delta U is Q plus W. Now, I don't know, frats. There's frats. Fraternities at the lake, right? Who's in a frat? Someone's got to be in a frat. Okay. What's the delta? The triangle is delta. All right. Yeah, that was my question. Ray, what does in the math world? Change. It means what minus what? Minus initial. That's what the delta means. Okay, and that'll help us out in a little bit to remember what the delta means. The delta U is Q plus W. So if I have, like Mariella here, I've got a beaker of ice, and it's just sitting there, right? And I want to identify it as my system. So you kind of have to seal it off and all that. And then you have all these different types of energy that would make up that system. What would be one of them? right? Because there has to be so much energy in that system. What would be something that could make up the energy in that system? Anybody help her? Ooh, kinetic energy is one, but you got to be more specific because kinetic energy is so general. You could say the energy of little molecules flying around, the energy of little molecules doing their vibrating thing, the energy of little molecules spinning, the energy of little molecules flying around. All those are kinetic energy. Think of any other one? Heat. Yeah, they have so much heat there. I mean, I know it's ice, but I could make it colder, right? I could suck some heat out of it, or I could add some heat to it, right? So heat's definitely another form of energy in there. You have energy in the bonds, right? There's a lot of different forms of energy. But if you add up all those different forms of energy, you get the delta U. Now, what's the U stand for? What is this? What's the name of delta U? Sylvia, do you know? Internal energy. It's internal energy. Internal energy. Okay, so there's a couple ways that you can change this internal energy. So internal energy is all the different forms of energy in our system that you want to pick on. There's a lot of different types of energy. But you add up all those energies, you get internal energy. The total sum of energy in that system. There's a couple ways you can mess with that internal energy. You can change it, either increase it or decrease it. Here's two of them. Really, that's it. Q and W. What are Q and W? Javier, you know what one of them are? Anybody help them? What's one of them? Work. W is the work. That's one way and that's a very odd way about changing the internal energy of a system is work. Who's had physics, general physics? Aldo's had general physics. What's the equation for work, according to a physicist? It's what times what? Distance times, you're close, force. Okay, distance times force. So, Alexa, don't move. Okay, don't move. Am I doing work? No, because Alexa isn't moving. Isn't that strange? I'm not doing any work. She has to move. So how the heck can systems like this thing do work? Something has to push against something else. It has to move out of the way. This is a really hard question. Yeah, something has to be pushing out of the way. But the only water's pushing against the glass, but the glass pushes back, so nothing ends up moving. All right, so no work there. Okay, this is what you got to do. You got to add some heat. And then the gas molecule, what happens to a gas if you add heat? It expands. So it's going to expand, and it's going to push against what? Yeah, the walls, but the walls aren't going to move. What is it pushing out of the way? What do you feel it? Air. It pushes the air out of the way. That's about the only type of work we're going to worry about. There's other types of work like electrical work, right? Like batteries, they do electrical work. But so that systems can lose energy by doing work, right? You can think of it's mostly though, like if you think of inside an engine, it's all this expansion work. The gas is exploding. It's pretty much all this expansion, pushing against something else. So the atmosphere is pushing against the piston. But you can do work. Okay, so that's one way to change internal energy is by a system doing work, like gasoline maybe or something, or gas expanding, heating it up. The other way to change internal energy is through Q. What's Q? This is the easy one. I thought this is the one you guys were going to guess. That's the heat. So we can add heat or suck heat out. That's another way to change internal energy. Q is our heat. How about the variables? What's the variable for energy? Joule, capital J. Right? What if I put Nick, kJ. What would that be called? Kilojoules. All right. Vanessa, we're going to see this later, but kJ over mol. You'd say kilojoules over moles, or kilojoules per mole. Here's one last variable set of units that we're going to see in table. We're going to be reading this all in tables, but what's this one? Kilojoules per mole Kelvin. Big K is Kelvin. Yeah. So we'll be seeing that in a little bit. Don't worry about it right now. I just wanted to give you a little hint what's coming up. Okay. What are the units for all this stuff in our equation? Delta U is energy, so it's got to be kilojoules or joules. Let's just pick joules. Q and W. You can only add apples and apples to get apples. They're both, everything's joules. Everything's energy. Yep, everything's energy unit. The second law of thermodynamics on human experience, just looking at what happens naturally. Like rocks fall, hot things get colder, right? You puncture a balloon and it pops. Ice melts, okay, in a warm room. What do all these things have in common? They're all thermodynamic. Yeah, these are all thermodynamic processes. Oh, okay, now we're getting into some ideas here. Releasing heat is a good one. That happens almost everything that Vanessa said. You hear what she said? Spontaneous. Almost everything that's spontaneous releases heat, but not all the time. You go to those first aid kits, right? Don't they have those little kits that you snap something and it doesn't get hotter, it gets colder? So there's some spontaneous reaction in there. It's just not exothermic, it's endothermic. So there's not everything releases heat, but most everything does. Javier's onto something there. But Vanessa said the word you're supposed to use. Thermodynamicists say, you could say natural, but you're not supposed to use the word natural. You're supposed to use the word spontaneous. They're all spontaneous. This is the harder one, though. What happens to the energy? It transfers, yes. Yeah, you're getting there. It's really hard to get to this. I think the easiest way to see it is the pressure one, right? It shoots out. Because there you can actually see it at the macroscopic, at the big level. Energy gets spread out. It's transferred, you're right, but it's spread out. It's dissipating or dispersed. All those words work. Dissipating, dispersed, spread out. That's what happens to energy in a spontaneous process. Okay? And we'll see that a little bit better in a little bit. Describe the second law with something like this statement. For any blank process, the blank must always increase. For any what process, Andrew? For any spontaneous process, this is a hard one, the what must always increase? It's entropy. You're right. It's entropy. The only one that we haven't really talked about it yet, but that's what's going to happen. Entropy is just energy getting spread out. That's all it is. Okay, let's take a closer look at energy, how energy is getting spread out. That happens in all spontaneous processes. Energy gets spread out, or entropy increases, same thing. Lewis, does ice melt in a warm room? Yeah, most definitely. Okay. Now, Victoria, if we take a closer look at this, do the cold water molecules give energy to the warm air molecules, or do the warm air molecules give energy to the cold water molecules? The warm air, right, gives energy to the cold water. Exactly. Energy gets spread out. It's concentrated in these warmer stuff, and it gets spread out. That's what natural is all about, right? it'd be fantastic, especially in Texas, if all the little hot air molecules in this room would just go up into that corner. But they don't, right? That's not natural. It's not going to happen. Entropy is a measure of how spread out the blank in a system is. How would you answer that one, Jessica Rojas? Entropy is a measure of how spread out the molecules it helps, but not necessarily. And I'll give you a little story on that. It's internal energy. Because heat is correct, but there's a better answer than heat, because heat's just one form of energy. There's a lot of different forms of energy. So by answering internal, P is the same answer as the heat, by the way. So those answers, even molecules, none of them are really wrong. It's just that internal energy is the best answer, because it's spreading out energy. For example, why would the molecules part be wrong? If you looked under your bed, if you're in the dorm, you look under your bed, I think they have tile floors, no carpeting, right? And you look under your bed in the dorm, and after about 2 weeks, there's a lot of dust. You look under there now, what do you see in regarding the dust? Dust bunnies, exactly, right? Now, the little dust is collecting up into these balls, right? Is that a natural process? Yes, it happened. It's a natural process. So that means molecules are gathering up. They're getting less dispersed. So entropy has nothing to do with the molecule. Entropy has to do with the energy getting dispersed. Okay? It doesn't have to do with the molecule. Okay? If let's pretend you're this big scientist dude and you're on the National Science Foundation. They're giving out all this money for research. And this guy's got this really good idea. He wrote it all up, has all the equations and everything, how you would build this engine and things. And what it does is, first you have to answer this question. Is there heat in the ocean? Yeah, because if you sucked out the heat, the water would turn into... Exactly, that's his plan. So you take the water in the ocean, suck out the heat, to run the engine, make the ship go. Then out the back, shoot ice. Now, it's really nice because you have global warming. It's going to help cool things down. Our ships go. You're the NSF evaluator. Would you go, or would you actually keep reading this article?
It takes energy to get it into the ice. So you can't.
You're on to something.
You can't take energy from a process that requires it.
You can't get something for nothing, right? You're going to look at that and say, it's impossible according to pick your law of thermodynamics. It ain't going to happen. It's not natural. Water sitting there on the ocean, right, in that heat and everything, it isn't going to spontaneously turn to ice. You can't get energy out of that. You can't make an engine out of it. You got to put energy into it, like Matthew said, to get it to work. All right. Third law of thermodynamics. This looks odd, this third law of thermodynamics, but it allows us to use tables to get numbers to plug into the equation that's coming up to predict spontaneity. That's really all it's about, is to get numbers and to get values. For example, you're going to measure. So where do you start? You start from the floor or something. Well, if you're going to measure these energies that we're going to be talking about, you've got to start from somewhere. So this is their definition. A crystal with no imperfections at 0 Kelvin has an entropy of what number? It's 0. They could have picked 12. They just got to pick something. And they picked 0. Okay. It doesn't matter. Let's just start measuring things. Free energy and predicting spontaneity. Okay. This is all the homework right here. They're going to want to know whether these yes or not. Okay. And you're supposed to use this equation. Delta G is delta H minus T delta S. Now, we already know the delta means what minus what? The change, which is final minus initial. So that's what the deltas were and all that. But how about any of the variables? Mallory, you recognize any of this stuff? Delta G, delta H, T, delta S? Yeah, there's our entropy. Good. Ray, see another one? Big T is temperature. Good deal. In fact, does anybody know what units you're going to have to use? Kelvin. Yeah. How low can you go in Kelvin? What's the lowest temperature? What's the lowest number? 0. Can you ever get negative numbers for Kelvin? No. The lowest you can get is 0 Kelvin. Why? You ever wonder why?
I don't think there's like negative 200 Celsius.
Absolute 0 is 0 Kelvin. Yeah, there's no more energy to suck out of there. What type of energy are we talking about? Heat. So what happens when you suck heat out of something? Think of it at a molecular level. It slows down. Everything slows down. Exactly. Pretty soon things stop moving, and then you can't suck any more heat out. So that's why you hit 0 Kelvin. Okay, we have delta H and delta G. Mariella, recognize one of them? Yeah, delta H is a change in enthalpy. We did that before, enthalpy. Pretty much heat at constant pressure. That's enthalpy. But delta G, anybody? Free energy. Technically, they want you to call it Gibbs free energy. Okay. There are units. Well, we'll get to the pretty much the units we don't really worry about because we're going to get all this stuff from tables. Right? The G for something. Let's take a look at something here. Diamond. What's the element that makes up a diamond? Carbon. Okay. Is that the same stuff? Carbon that you have a little campfire, get that black stuff? Yeah. It's charcoal. It's just a different structure. You don't have this nice crystalline thing going on there. So you could have charcoal. Okay. Now, the question is this a spontaneous process? Can your diamond spontaneously turn into charcoal?
No.
Okay. Now, you can do the equation. That's what this equation is for. It can predict whether, hey, this will happen or not. And it will. So you do the math. No one argues with it. Diamond will turn into charcoal. But here's the kicker. A thermodynamicist's point of view, is spontaneity like that? No. And they have no idea how much time. They're just saying it will happen. So at some point in time, I don't know how many millions of years, or I don't know how long, that all these diamonds in your rings, they will be a hunk of charcoal. Now you can speed up the process by, especially with heat, having a propane torch or something. But it takes a little while, and it'll work. Okay, it will happen. Okay. So let's see how to use this equation here. When it will happen. What's that? The reverse would be non-spontaneous. Charcoal will not spontaneously turn into diamond. Okay? Now, I'm talking about a hunk of charcoal sitting out here on Pablo's finger, right, for eons. I'm not talking about a hunk of charcoal under how many miles of sediment under really high temperature and really high pressure. Look at all the energy you're putting into the system, right? I'm not talking about that. So I'm talking about a diamond ring on Pablo's finger sitting here at room temp for eons. It will turn into charcoal, right? So under those conditions, the process would be non-spontaneous. You're not going to, his little hunk of charcoal is going to spontaneously turn into a diamond. You have to put a lot of energy in. Okay. So how do you use this equation? How do you figure all this stuff out? Well, let's start at the very top here. When what is less than 0, it's spontaneous. Which variable? Delta. That's the big one. That's the one we're all interested in. What's the delta G? Is it positive or negative? If it's negative, it's going to be spontaneous. Does that mean it's going to happen immediately? No. But it will happen sooner or later. Right. How do we get numerical values for all this stuff? We want to get numerical values for delta S, P, and delta H. I guess, Javier, they have to tell us the temperature, but how do you get numerical values for delta H and delta S? We're going to use tables, right? And no one brings their book to class anymore, right? I mean, look at this. Oh, some people did. Now, if you don't, you're going to have to Google. We'll talk about all this. But, okay. So we're going to use tables to get these values. You get the tables for delta H, you get the tables for delta S. Now, what numbers are you looking up here? If you have a reaction, what's initial and what's final? The reactants are initial. That's where we're starting out. The products are final. So if you want to get, I don't care, delta S for that reaction, do final minus initial. Add up the delta, find them in the table, look at the delta S for every product, add them all up, subtract out the delta S for every reactant. It's final minus initial. And then you get whatever you get, you get. Do the same thing for delta H. Do the math in the equation, and you can get delta G for the entire reaction. Or just use the delta G table in the first place, right, for products minus reactants. Okay. A reaction is more likely to, now looking at the equation. The equation, Nick, is the hint. That delta G is delta H minus T delta F. This is the hint. A reaction is more likely to be spontaneous if it is exo or endo. Exo, because delta H would then be negative. Right? Because look at the math. Right? Because delta G will more likely be negative if delta H is negative. It doesn't have to be. Right? You remember those spontaneous processes, the bags getting colder, right? Those first aid bags. So if that's the case, if it is endothermic, that negative T delta S part must be huge to overcome the positive delta H. It happens. Okay, but it's more likely if you have exothermic reaction. And the change in entropy is positive or negative, Vanessa? Stop. Vanessa, sorry. How come I haven't picked on you all day? Oh. What did you say, Vanessa? Entropy should be, if it's negative, look at the equation, it's minus T delta S. It has to be positive, all right? Because it's minus T delta S. So you lose your negative component if delta S is negative, because you have that minus sign out front. And the reaction occurs at really high or really low temp. Anybody? Really high. All right, really high temp. Okay. That's the most likely way to get spontaneous reactions. Oh, there's one last thing I forgot. How can you predict entropy for a reaction? Because that's going to be, that's the only one you can really predict. You can't predict, looking at a reaction, oh, that's exothermic, oh, that's endothermic. Not unless you've actually seen the reaction happen. You can't predict it. But if you're given the reaction written there, you see all the subscripts, gases, and liquids. Say, oh, delta S is huge. Oh, delta S is negative. Delta S is positive. You do that by looking at the gases, little subscript G's. Because entropy is what spread out? What? Internal energy, or energy. The more spread out energy is, oh man, more delta S is. Well, solids, they don't. Now you take a container. The solid just lays on the bottom. Take a container. The liquid just lays on the bottom. They're not going to spread out for you. But gases immediately flip energy as much as possible. So that's pretty much the only thing you look at. Am I generating a lot of gas? If you are, oh man, energy is going to be really dispersed. Delta S is going to be a big positive number. If all my gas is reacting, I don't have any, then delta S is going to be a big negative. And we'll take a look at that pretty much right now in this question right here. We want to calculate delta S0. Oh, shoot. Matthew, what is that? Superscript 0. What did they put that there for? Not initial. Does anybody know? Oh, it means some degrees. It means a particular degree. It means 25 degrees Celsius and exactly 1 atmosphere. They call that standard conditions. Because if you change those, you can't use what anymore? The tables. So you're going to see this superscript 0 a lot. It just means use the tables. You're at standard conditions. Okay. So they want to find delta S0 for that reaction. So we have to add it all up for the product, subtract out the delta S for all the reactants, and we'll have our answer. So products, we have like CO2, we have water, right, to put in the number. We also have to look up the reactants. We have C2H4, and we've got O2. So I'm going to dish my appendix out. Now, like I said, if you don't have your book, you could be Googling this stuff. Page 743? Oh, I look in the back appendix. Where is this stuff? You could be Googling delta S for all this stuff. Here it is. But remember, on the exams and quizzes, you can't be Googling. You have to learn how to use this table, so I'll just be photocopying it. So I'm just going to hand it to somebody here. So what we want to do is find CO2 and the delta S for it. But it needs to be CO2 gas. So we're going to find the carbons, right? And see if you can find CO2. It has to be gas. And we need a delta S number. It's 213.7. That same carbon area, let's find the C2H4 delta S number. 219.2. Okay, now let's just hand it to somebody else. Or to Lewis. Okay. Lewis, see if you can find, now we need H2O. But it needs to be H2O liquid. You probably have to look in the hydrogen area. H2O liquid. 69, and that's the delta S number, right? Okay, now you have to look up O2 gas, the delta S number. 205. Okay. Now, does anybody see? They read the numbers right, I'm pretty sure. Where did we screw? Stoichiometric coefficient. What are you supposed to do with the stoichiometric coefficient? Powers, or do you put them out front? Out front. Because remember, like, look at the CO2. There's two of them. So when you add up the delta S for all of the products, you have to add up CO2 twice. So there has to be two of them. The water liquid has to be 2 of them. The oxygen has to be 3 of them. It's products minus reactants. It always has to be. Remember, it's final minus initial. These deltas mean final minus initial. You have to add up the delta S for all the products. So you don't, exponents aren't used for adding up. Exponents are, like an equilibrium expression. See, now, Lewis, you have the book, though. What units are we supposed to put? That delta S, what units do they have on it in that table? What units? Yeah. So you don't need to memorize it. Just see what it says in the table. All right? Okay. Let's see what we get here. $267. Okay, good deal. I hear several folks agreeing, so that's got to be it. Yeah, so somewhere on there. Now, we're not quite done because the question says, does the entropy increase or decrease? Well, it's negative. Minus initial is a negative number. So that means final is a lot smaller than initial because you got a negative number. So delta S decreased, right? Delta S decreased. Delta S decreased. Now, the second part was, or the third part, I guess, as you expect. Do you expect delta S to decrease? So you're only supposed to look at what to predict with delta S? What state? Gas. So let's figure out the gas molecules on this side. Let's figure out the gas molecules on this side and see what happened with the gas molecules. So on the reactant side, how many gas molecules do I have? 4. On the reactant side, C2H4 and 3 O2s, everything's gas. I've got 4. Everything's a gas molecule. On the product side, just 2. So what happened? Do I end up with more or less gas molecules? Ended up with less. Energy is less dispersed, less entropy. So a big negative number. It should be. Okay, so it does agree. Agrees. Less gas. Okay. Here's this type of question I think you'll like in the homework. I bet you there's not a whole lot of it. Your non-spontaneous or easily reversible. And the first one, Andrew, we've got a reaction, and they say delta G 479 kilojoules. Well, what would you say? Spontaneous, non-spontaneous, or easily reversible? Not spontaneous. It's a big positive number, right? Yeah, so it should be non-spontaneous. How about the second one, Lewis? Positive 110 kilojoules. Lewis. Positive 110 kilojoules. Spontaneous, non-spontaneous, easily reversible. That's not, but it's not small. This guy is small. Yeah, still non-spontaneous. Now the 2.6, he's close to 0. So that one you would say is easily reversible. Okay. We need to see a what to say spontaneous? A big negative. Yep, big negative. All right. Here we go. Let's get delta H 0. Yes, yes, sir. Yeah. Put a negative here, still easily reversible. It's just close to 0.
So how do you know if it's easily or spontaneous?
Easily any number less than 5. Right? Between 0 and 5. No, it can be a negative 2.6. That's still close to 0. So that's easily reversible. I would. They're never going to cut it that close. They're going to have really big numbers in the hundreds, or they're going to have a 0.6 or a 2. They're not going to make you judge. Okay. We got to get delta H0, and we need to get delta G0. Using these tables. So, product minus reactant. We got to do that for delta H. We got to do that for delta G. Product minus reactant. And let's just kind of fill in the compound. We have CO2, and HCl is the other product. And the reactants, we have COCl2 and H2O. We've got to make sure we look up the right ones, like H2O is liquid. So let's move our table around here. CO2, let's give it, let me get in the back here. You guys wake up. CO2, Javier, it needs to be a gas, and we need the delta H number for it. So it should be the carbon. And when with the carbon, CO2 gas, and we need a delta H number. It's negative. Negative 393.5. And now how about the CO2 gas, but the delta G number? 394.4. Okay, pass it to Andrew there. Andrew, since we're in the carbon, see if you can find a COCl2 in that carbon area. COCl2, and we need the delta H number. Negative 224. Negative 220. So that's COCl2 gas, and that's the delta H number. Oh, 0.1. And then how about the COCl2, but the delta G number? Negative 205.9. Okay. Now, Jasmine, keep going here. Let's look up HCl, and it needs to be gas. So I bet you have to look in the chlorine area. So use Andrew's book there. Keep passing it down. So you can find the chlorine area. It should be alphabetical. He's in the carbon. So see if you can find HCl gas. HCl gas, the delta H for it. You see what we're looking for? Find the chlorine. Find the chlorine. Here's the chlorine, right? And find HCl gas. Then go over to the delta H column. Negative 92 point what? 31. Okay, now find the HCl gas. Negative 95.3. Okay, now hand it over to Amanda there. Okay, Amanda, we need H2O. It needs to be liquid, not H2O gas. We need H2O liquid and the delta H number. -2. Now the H2O liquid, but delta G number. -2, 8.6. Okay. Now, do you see anybody where I screwed up? Yeah, I figured there'd be at least one stoichiometric coefficient in there somewhere, right? And the HCl is the only one, so make sure we have a 2 here. Make a different color, make sure you can see it. Got to have a 2 here, have to have a 2 there. Now, Amanda, you still have the book. What are the units we're supposed to put on delta H once we finally get it? In that delta H column. Kilojoules over moles. And how about the delta G column? Yeah, okay, they're both the same. So you do your math, get your answer, products minus reactants. Okay. Oh, yeah, should be -237.1. Oh, H2O liquid in the delta G column. It should be what? Okay. Okay. So we're about out of time, but it's not too bad. Mm-hmm. Well, 2 times a negative number is still negative.
Oh, okay.
Right?
So it's not like -92 times -92?
No, you're adding -92 and -92.
Okay, so you got negative.
Yeah, it's like -92.31 plus -92.31.
Oh.